The void between the stars is not empty. It is a canvas stretched across the immeasurable darkness, painted with light from distant suns and the occasional whisper of wandering worlds. Among these travelers, few have ever crossed our solar threshold, and fewer still have dared to challenge our understanding of cosmic order. 3I Atlas arrived as a phantom, a silent interloper moving with a trajectory that marked it unmistakably as an interstellar visitor. Observatories first noticed its hyperbolic path, an escape from the gravitational confines of any single star, a fleeting apparition that belonged to no one system, yet now passed through ours. Then came the shattering. Without warning, the object fragmented, as though some hidden stress had finally overcome an ancient cohesion, and its debris began racing outward from the central mass of the former whole. For astronomers peering through telescopes, the spectacle was both breathtaking and terrifying. Countless pieces of an interstellar puzzle scattered, each moving in defiance of every calculated expectation. The destruction of 3I Atlas was not silent. Light, reflection, and radiation cascaded from the fragments, each flash a signature of violent forces at work in the deep vacuum. This breaking apart was more than a mechanical failure. It carried the aura of the inexplicable. How could a body that survived interstellar distances hundreds of thousands of years traversing the void disintegrate with such suddenness and precision? What forces, unseen and immense, could act upon this object, shaping its death as it entered our solar system? Even the brightest minds in astrophysics paused, their models strained against this anomaly. And yet, there was beauty in the chaos. The debris, illuminated by sunlight now for the first time in its cosmic journey, traced arcs across the blackened sky, a transient constellation of destruction that humanity would witness as both warning and wonder. Each fragment carried with it a story, a record of materials formed in alien systems, shaped by processes we could scarcely imagine. The disintegration of 3I Atlas was not merely an event. It was an invitation to question, to peer deeper into the forces governing matter and motion beyond our Sunday. As the fragments accelerated toward the inner solar system, a subtle tension gripped every observatory and lab that tracked them. The pace was neither rapid nor leisurely. It was deliberate, almost purposeful, in its relentless adherence to a path that humans could plot but barely comprehend. With every observation, every calculation, 3I Atlas demanded a reckoning with the unknown, forcing us to confront not only the mechanics of its collapse, but the vastness of interstellar mystery itself. It was a harbinger, a shattered messenger from the cosmos, racing toward the very worlds we inhabit. The first hints of catastrophe emerged not in grand headlines or sudden alerts, but quietly, almost imperceptibly, within the meticulous logs of astronomers scanning the heavens. Light curves graphs of brightness over time began to wobble erratically. Where once 3I Atlas had glided predictably, the readings now betrayed sudden dips and spikes, as if the object itself were breathing in jagged rhythms or fracturing under invisible pressures. At first, these anomalies were dismissed as instrumental noise, calibration errors, or the usual cosmic background interference. But soon, the pattern persisted, undeniable and perplexing. Telescopes across the globe, from Mauna Kea in Hawaii to La Silla in Chile, trained their lenses with renewed urgency. Observers noted the scattering of light, subtle at first, then more pronounced, signaling that the interstellar visitor was fragmenting. Unlike comets familiar to our solar system, whose tails flare and flare predictably under solar radiation, 3I Atlas exhibited irregular brightening along unexpected vectors. Each new observation deepened the puzzle. Fragments appeared to separate at varying speeds, some accelerating faster than physics or at least conventional interpretations would allow. Initial photometric studies hinted at an intricate interplay of forces. Outgassing, a phenomenon typical of comets where volatile ices sublimate under the warmth of a star, could account for some propulsion of debris. Yet 3I Atlas had long been far too distant and cold for solar heating to dominate its motion in this way. Moreover, the velocities observed in the newly freed fragments exceeded what any outgassing model could justify. Instruments that measured spectral signatures detected flashes of metallic and organic compounds, a composition unusual for cometary bodies and suggestive of a far more complex history. By the time news of the fragmentation reached broader scientific circles, concern had escalated from curiosity to cautious alarm. Each debris fragment, while small on cosmic scales, carried sufficient mass to pose potential planetary hazards if trajectories intersected with Earth or nearby celestial bodies. The realization crystallized in late-night calculations and simulations across observatories. 3I Atlas was no ordinary visitor, and its disintegration introduced a dynamic we had not anticipated. Amid this upheaval, the human element emerged. Astronomers and astrophysicists, many of whom had spent decades charting distant stars and comets, felt a mixture of exhilaration and dread. There was awe at witnessing a cosmic event of such magnitude in real time, and anxiety over its unpredictable consequences. The sky itself seemed to signal an urgent reminder: the universe is vast, indifferent, and occasionally violent, and even our most sophisticated models and instruments are but modest tools against its scale. The first signs of 3I Atlas's fragmentation were a whisper of catastrophe, subtle yet insistent, demanding attention and immediate investigation. The story of 3I Atlas's discovery begins with the steady hum of automated sky surveys, scanning vast swaths of the heavens night after night. It was during one such survey, years before its fateful fragmentation, that a faint point of light appeared moving against the familiar backdrop of stars. At first, it was indistinguishable from countless other transient detections, a minor fluctuation, a distant asteroid perhaps, or a mere instrumental artifact, yet its trajectory quickly set it apart. Unlike objects bound to the Sun, this body exhibited a hyperbolic orbit, a straight-line path through space that no planetary gravity could confine. It was, unmistakably, an interstellar visitor. Astronomers scrutinized its path, calculating velocities that exceeded any typical solar system object. Its inbound speed and inclination suggested that it had traveled for millions of years across the dark expanses between stars, a silent wanderer from a distant system. Initial observations were cautious. It was small, faint, and distant. But each subsequent night, the object revealed more of itself: subtle brightness variations, a slight elongation, and then the first hints of a nucleus unlike ordinary comets. Scientists compared notes across continents, plotting its course, sharing spectral data, and preparing for what could be a unique opportunity to study matter formed outside our solar neighborhood. The people behind these observations were as varied as the instruments they wielded. Teams of astronomers, many operating robotic telescopes, pored over pixel arrays and light curves. Some were veteran comet hunters, familiar with the patterns of sublimation and rotation, while others specialized in interstellar dynamics, seeking anomalies that could challenge established physics. Each contribution was meticulously catalogued, from the first detection to the repeated confirmation of its hyperbolic escape trajectory. Even before fragmentation, 3I Atlas commanded attention for its curious behavior. It did not fully conform to models derived from comets or asteroids. The initial fascination was compounded by its subtle anomalies. Light curves exhibited irregular flickers, not consistent with tumbling or simple outgassing. Observations from multiple sites confirmed these deviations, ruling out equipment error. the anticipation grew. Here was an object from another star system, carrying chemical and isotopic signatures that could illuminate the processes of planet formation and cosmic chemistry far beyond our solar system. Scientists tracked each movement with precision, aware that even the smallest observational detail might reveal profound truths. Ultimately, 3I Atlas's discovery was a testament to patient observation, technological precision, and international collaboration. From the faint streak caught on a sensitive detector to the global coordination of astronomers calculating its interstellar trajectory, it became clear that this object was extraordinary. Long before it shattered, 3I Atlas had already rewritten expectations, not merely a distant wanderer, but a messenger from the cosmos, carrying secrets from the uncharted reaches of space toward a solar system unprepared for its eventual, violent arrival. As 3I Atlas journeyed closer to the Sun, subtle anomalies began to emerge that defied early expectations. Unlike comets familiar to Earth-bound observers, whose brightness and tail behavior follow relatively predictable models, this interstellar visitor displayed a series of deviations that prompted deep scrutiny. Its trajectory, although hyperbolic, showed minute irregularities, slight bends, and accelerations inconsistent with gravitational calculations alone. Each new observation deepened the sense of mystery. The object seemed to respond to forces unseen, as though the very fabric of space were nudging it along uncharted paths. The brightness fluctuations further puzzled scientists. Observers recorded irregular pulses, brightening and dimming in ways that could not be accounted for by rotation or outgassing typical of solar system comets. Spectroscopic analysis revealed inconsistent emission lines, hinting at materials both familiar and foreign, silicates and organics mingled with metallic compounds rarely seen in ordinary comets. The interplay of light and shadow along the object's surface suggested a complex, perhaps layered, internal structure. Some researchers speculated about a porous, almost skeletal composition held together tenuously over millennia of interstellar travel. Outgassing patterns also challenged standard models. While sublimation of ices under solar radiation was expected to produce a relatively symmetric cometary tail, 3I Atlas exhibited asymmetric jets of gas and dust, shifting unpredictably. At times, these emissions seemed almost self-directed, accelerating fragments along unexpected vectors. Even the most sophisticated simulations struggled to replicate this behavior. Some scientists hypothesized that rotational spin-up, induced over centuries of exposure to cosmic radiation and tidal forces, might have created structural stress, while others suggested more exotic influences, interactions with interstellar magnetic fields, or even unknown physical processes acting upon the object during its journey. The cumulative effect of these anomalies was profound. Where once 3I Atlas was merely a rare visitor, it now became a riddle, a test of human understanding of cosmic mechanics. Each telescope observation, each spectral reading, each calculation of position contributed to a growing awareness that this object would not conform to expectation. Its subtle deviations hinted at a hidden complexity, a story encoded in light, motion, and composition, waiting for observers to decipher. By the time the first fragments separated, the scientific community had already been primed by weeks of puzzling behavior. Researchers were not merely witnessing the breakdown of a cometary body, they were observing a phenomenon that questioned long-held assumptions about interstellar objects, their resilience, and their interactions with the solar system. Every anomaly, every unexpected flicker, foreshadowed the dramatic fragmentation that would soon define 3I Atlas's journey toward the inner solar system. To comprehend the significance of 3I Atlas, one must first place it within the sparse but growing catalogue of interstellar visitors. The most famous among these is Oumuamua, discovered in 2017, which startled astronomers with its elongated shape and unexplained acceleration, prompting debates over whether it was a comet, asteroid, or something altogether stranger. Unlike familiar solar system comets, these interstellar objects are rare, fleeting, and difficult to study in detail. 3I Atlas arrived with characteristics both echoing and surpassing these earlier anomalies, amplifying its intrigue. Historical comparisons are illuminating. Oumuamua offered a brief glimpse into matter formed outside our Sun, yet it was enigmatic precisely because of its simplicity in terms of observational opportunities. 3I Atlas, by contrast, presented an object not only approaching the inner solar system at high velocity, but one that actively defied expectations through fragmentation, asymmetric debris patterns, and complex spectral signatures. Observers immediately drew parallels to the earlier visitor, noting both similarities in trajectory and stark differences in behavior. While Oumuamua remained intact, 3I Atlas splintered violently, revealing a wealth of structural and compositional information hidden beneath its surface. The rarity of such visitors cannot be overstated. Interstellar objects pass through our solar system like whispers through a corridor, brief, ephemeral, and often invisible to most telescopes. Their detection relies on a combination of precise survey coverage, sensitive instrumentation, and fortuitous timing. When such an object is discovered, every photon matters. Every observation can shed light on processes and materials that originated light years away, perhaps in a system unlike our own. 3I Atlas, with its massive size, hyperbolic trajectory, and sudden disintegration, represents the most accessible and informative interstellar encounter in modern times. This historical perspective also frames the scientific shock that accompanied its shattering. Astronomers were not only confronted with an unprecedented event in terms of size and complexity, but also with the realization that our predictive models of interstellar object behavior were incomplete. Each historical comparison, from long-period comets in our solar system to Oumuamua's brief visit, served as a backdrop against which 3I Atlas stood as both continuation and disruption. It was a rare alignment of cosmic rarity and observational readiness, demanding rapid analysis, cross-disciplinary collaboration, and a recalibration of expectations about the nature of interstellar debris. In reflecting on these prior encounters, scientists recognized that 3I Atlas was both a teacher and a challenge. Its arrival offered the possibility of understanding the chemical and mechanical history of a star system far beyond our own, while simultaneously exposing the limits of current astrophysical models. The historical context underscored the uniqueness of the moment. Humanity was witnessing a tangible piece of another world, disintegrating in real time, scattering clues across the void toward a planet unprepared for its cosmic message. The fragmentation of 3I Atlas sent shockwaves through the scientific community, reverberating far beyond the observatories that first tracked its hyperbolic journey. Experts who had dedicated careers to the study of comets, asteroids, and interstellar objects found themselves confronted with phenomena that defied their most trusted models. The degree of structural failure, coupled with the unusual trajectories of its fragments, suggested forces acting on the object that were neither anticipated nor easily explained. Standard cometary physics seemed inadequate, and the discrepancy between expectation and observation became a focal point of both awe and unease. Physicists struggled to reconcile the data with conventional paradigms. The acceleration of certain debris fragments exceeded what could be accounted for by known outgassing processes or gravitational perturbations from the Sun and planets. Rotational spin-up, often invoked to explain comet fragmentation, provided only partial insight. The irregular distribution of mass and energy suggested a more complex interplay of internal and external forces. The light curves from multiple telescopes continued to fluctuate in unexpected patterns, revealing intermittent brightening events inconsistent with simple mechanical fracture. Each anomaly compounded the impression that 3I Atlas was not merely unusual, it was potentially paradigm-breaking. Moreover, the chemical signatures detected in the debris amplified the astonishment. Spectroscopy indicated the presence of metallic compounds alongside organic molecules, a combination rarely observed in cometary bodies and indicative of processes occurring in environments vastly different from our own solar system. Some fragments displayed reflective surfaces with spectral characteristics suggestive of unusual crystalline structures, hinting at a history of thermal and radiation exposure that challenged existing models of interstellar object formation. For the scientific community, the data painted a portrait of complexity and resilience, a body that had traversed the void for millennia, only to succumb in dramatic, unexpected fashion upon entering the inner solar system. This shock was compounded by the implications for observational methodology. The very fact that 3I Atlas had defied prediction highlighted gaps in the monitoring and modeling of interstellar bodies. Where previously interstellar visitors were considered rare curiosities, this event underscored the potential hazards of underestimating the dynamics of fast-moving, massive objects. Collaborative discussions erupted across international observatories, with scientists debating the plausibility of natural explanations versus more exotic forces. Each meeting, each published preprint, carried an undercurrent of tension. Could humanity's current understanding of cosmic mechanics truly accommodate what was unfolding? The shock of 3I Atlas's behavior extended beyond theoretical considerations. It was emotional, philosophical, and existential. Here was a tangible messenger from another star system, shattering with a suddenness that defied expectation, scattering pieces across the solar system and challenging every assumption about resilience, structure, and cosmic inevitability. It was a stark reminder that the universe, in its vastness and indifference, can produce events of profound complexity that both enlighten and unsettle. Scientists were not merely observing fragments of rock and ice, they were witnessing the limits of human comprehension stretched thin by the relentless, mysterious forces of the cosmos. As the debris from 3I Atlas continued its dispersal, the focus of observation shifted toward the velocities of individual fragments. Early measurements revealed something astonishing. Many pieces were accelerating at rates far beyond what conventional cometary fragmentation models could predict. Where typical solar system comets exhibit modest post-fracture dispersal due to sublimation or rotational forces, 3I Atlas fragments seem to possess kinetic energy imparted by mechanisms yet unknown. Each fragment traced a path that hinted at hidden dynamics, interactions with solar radiation, interstellar magnetic fields, or perhaps internal pressures released in ways that defied expectation. The acceleration patterns were meticulously recorded by a network of telescopes, both ground-based and spaceborne. Observers noticed that some fragments moved in near-parallel trajectories, while others diverged sharply, creating a chaotic yet measurable debris field. Infrared imaging revealed temperature gradients along the fragment's surfaces, suggesting differential heating or outgassing, though calculations showed that conventional sublimation could account for only a fraction of the observed motion. Scientists began to explore more speculative forces. Could some fragments have contained volatile materials trapped under pressure for millions of years? Could interactions with the sparse interstellar medium have subtly augmented acceleration? Further analysis focused on rotational dynamics. The fragments exhibited signs of tumbling, spinning unpredictably, and in some cases, rotation appeared to accelerate as the body moved closer to the sundial. Such spin-up could contribute to the propulsion of fragments, yet the irregularity and magnitude of the velocities indicated that additional forces were in play. Some theorists considered the possibility of previously unmodeled micro-explosions, internal stresses releasing energy in sudden bursts, or even electromagnetic interactions with charged solar wind particles. Each scenario, while intriguing, carried uncertainties that demanded careful observation and verification. Beyond the mechanics, the high-velocity debris posed both observational and existential questions. From an observational standpoint, tracking such rapidly moving fragments required unprecedented coordination, rapid data analysis, and predictive modeling that accounted for minute deviations. From a human perspective, the sheer speed and unpredictability intensified concerns about potential collisions with planets or other solar system bodies. While the odds of a direct impact with Earth remained low, the knowledge that fragments were accelerating at unexpected rates transformed abstract risk into a tangible consideration for planetary defense planning. In essence, the high-velocity behavior of 3 Atlas fragments redefined the very framework through which interstellar objects could be understood. No longer merely passive wanderers from distant stars, these fragments demonstrated dynamic responses to forces both known and mysterious. Each new measurement, each plotted trajectory, reinforced the sense that humanity was observing a cosmic phenomenon that challenged assumptions, demanded rapid adaptation, and offered a rare, if unsettling, window into the physics of objects that have traveled light years untouched, only to reveal their complexities in our solar backyard. Beyond motion, the composition of 3 I-Atlas's fragments became a central focus, revealing a spectrum of materials that seemed almost otherworldly. Spectroscopic analysis, conducted across multiple wavelengths from ultraviolet to infrared, detected unexpected metallic signatures alongside more familiar silicates and organic compounds. This unusual mixture challenged established paradigms. Comets from our solar system typically exhibit a predictable composition dominated by water, ice, silicates, and simple organics. The presence of metallic elements, some in reflective crystalline forms, suggested a history shaped by processes beyond the conventional cometary model. Each fragment acted as a microcosm of interstellar history. Light reflected off jagged surfaces, revealing patterns that implied differentiation, a separation of materials that occurs over prolonged thermal or gravitational evolution. Some pieces emitted spectral lines consistent with rare isotopes, hinting that they formed in environments with distinct nucleosynthetic histories, possibly in a stellar nursery light years away. This complex chemical fingerprint positioned 3 I-Atlas not merely as an interstellar wanderer, but as a relic of alien planetary or protoplanetary processes, a carrier of cosmic history from a distant system. Infrared observations added further intrigue. Thermal maps of the fragments showed irregular heat distribution, suggesting heterogeneity in density and composition. Some regions absorbed sunlight and emitted infrared radiation efficiently, while adjacent areas remained comparatively cooler. This uneven thermal behavior hinted at a porous, layered structure, perhaps containing pockets of volatile ices or embedded metal-rich cores. Scientists postulated that these variations could account for some of the unexpected acceleration, as differential heating and outgassing created micro-propulsive effects. The diversity in spectral characteristics also raised the possibility of more exotic explanations. Certain emission features did not match known solar system materials, leading to speculation about amorphous metals, complex organometallic compounds, or unusual crystalline structures forged under conditions far removed from those in our own planetary neighborhood. Each fragment, in essence, became a laboratory for studying processes otherwise inaccessible to terrestrial instruments, a tangible connection to the chemistry of distant stars and their circumstellar disks. Ultimately, the spectral mysteries of 3I Atlas emphasized the dual nature of the observation, both empirical and philosophical. Scientifically, the fragments offered data that could refine our understanding of interstellar object formation, migration, and resilience. Emotionally, they served as reminders of the universe's vast complexity, carrying with them materials that had survived eons in interstellar space, only to arrive in our solar system and reveal their hidden intricacies. In this interplay of light and matter, observers glimpsed not only a physical anomaly, but also a profound narrative of cosmic history, written in the language of atoms and photons. As 3I Atlas's fragments continued their dispersal, the looming question of trajectory became paramount. Observatories worldwide coordinated to map the paths of the debris, using high-precision astrometry to predict the possible intersection points with planets, moons, and other solar system objects. Calculations indicated that while the majority of fragments would continue on hyperbolic escape trajectories, some pieces were on orbits that could intersect with the inner solar system, raising concerns about potential impacts with Earth or Mars. The very idea that material from another star system could reach our neighborhood with measurable probability sent ripples of urgency through the scientific community. The challenge lay in the inherent uncertainty. Fragments were small relative to planetary scales, yet their velocities were extraordinary. Even minor deviations due to outgassing, solar radiation pressure, or gravitational interactions could result in significant differences in impact probability over time. Modeling each piece required integrating data from multiple observatories, accounting for measurement errors, and applying advanced simulations to project trajectories months, even years, ahead. Despite these efforts, the complexity of interactions and the chaotic dispersion of fragments meant that predictions remained probabilistic rather than deterministic. As the debris cloud moved inward, its composition compounded concerns. Metallic fragments, with densities greater than typical cometary material, possessed significant kinetic energy. Organic-rich fragments, while less dense, could survive atmospheric entry, creating meteor showers with unpredictable brightness and distribution. Even without direct impacts, such debris could pose challenges for spacecraft, satellites, and orbital infrastructure. The international community of astronomers, planetary scientists, and space agencies began planning contingency observations, refining models, and sharing rapid updates to ensure early detection of any fragments on potentially hazardous courses. The visualization of this threat transformed abstract calculations into a tangible narrative. Diagrams showing arcs of debris converging toward Earth or Mars captured public attention, though scientists emphasized the low probability of catastrophic events. Nevertheless, the mental image of extraterrestrial fragments, accelerated over light years and now careening toward familiar planets, underscored both the fragility and the interconnectedness of our solar system. It also highlighted the broader philosophical dimension. Humanity, long accustomed to a relatively isolated cosmic perspective, was being confronted with matter that had originated from a distant star, carrying its own history, now entering our immediate neighborhood with unpredictable consequences. Thus, the trajectory of 3I Atlas's fragments became both a scientific puzzle and a visceral reminder of cosmic scale. The paths were mapped with precision, yet each calculation carried a tension born of uncertainty. a delicate balance between empirical rigor and the awareness that, in the vastness of space, even small fragments from distant worlds could traverse unimaginable distances to reach the doorstep of our planetary home. The influx of fragmented debris from 3I Atlas demanded the full capabilities of modern astronomical instrumentation. Hubble Space Telescope, with its unparalleled resolution, turned its attention to the brightest fragments, capturing detailed images that revealed surface textures and subtle jets of sublimating material. Ground-based observatories complemented these observations with wide-field imaging, providing context for the spatial distribution of the debris cloud. Infrared telescopes, such as the Spitzer Space Telescope, mapped thermal emissions, revealing heat patterns that hinted at internal composition variations and volatile retention across the fragments. Each instrument contributed a piece of the puzzle. Optical telescopes measured light curves, allowing astronomers to estimate rotational periods and fragment sizes, while spectroscopy across multiple bands identified the elemental and molecular makeup of the debris. Radio telescopes, attuned to specific atomic transitions, detected the presence of gas plumes, some enriched with organic compounds uncommon in solar system comets. This multi-wavelength approach offered a comprehensive portrait. 3I Atlas was not a homogeneous body, but a complex assembly of materials, each fragment telling a story of interstellar evolution, cosmic pressures, and thermal histories that spanned millions of years. The data also revealed intricate motion patterns. Infrared mapping showed differential heating, suggesting that some fragments were denser or more reflective than others. This heterogeneity contributed to non-uniform acceleration, complicating trajectory predictions. High-precision tracking allowed teams to model the debris field dynamically, accounting for gravitational perturbations from the Sun, planets, and even other fragments within the cloud. These models underscored the importance of continuous observation. A minor miscalculation in velocity or direction could significantly alter impact probabilities over months. Beyond the mechanical data, the instrumental insights hinted at deeper mysteries. Certain fragments exhibited brightness variations inconsistent with expected albedo or rotation, implying reflective or metallic surfaces not previously catalogued in known interstellar visitors. Others emitted sporadic gas jets that could not be explained by conventional sublimation. For scientists, these anomalies suggested that 3I Atlas contained materials or structures not typically found in cometary bodies, possibly remnants of a distant planetary formation environment or processed matter from a star system unlike our own. Through these combined observational efforts, humanity gained an unprecedented window into an interstellar object's inner workings. Each telescope and sensor transformed photons into knowledge, revealing a fragmenting world hurtling across space, a witness to forces both familiar and alien. The images, spectra, and thermal maps were more than data. They were the fingerprints of a distant history, delivered through light and motion, challenging our understanding of how matter survives, transforms, and interacts beyond the confines of the solar system. To understand why 3I Atlas shattered so dramatically, scientists turned to the cosmic forces that govern celestial bodies, examining both familiar mechanisms and speculative influences. One of the first considerations was tidal stress, the differential gravitational pull exerted by the Sun and planets as the object approached the inner solar system. For objects on hyperbolic trajectories, tidal forces can stretch and twist, especially if the internal cohesion is marginal. In 3I Atlas, such stresses may have acted in concert with pre-existing fractures or weak points, priming the object for catastrophic fragmentation. Rotational spin-up presented another compelling mechanism. Over millennia of interstellar travel, Subtle torques induced by uneven radiation pressure or asymmetric outgassing can gradually increase rotation rates. When the centrifugal force at the surface exceeds the material strength, structural failure becomes inevitable. Observations of fragments suggested that portions of 3I Atlas were spinning rapidly prior to breakup, lending credence to this hypothesis. Unlike typical solar system comets, which generally exhibit modest rotation, the interstellar journey of 3I Atlas may have amplified these effects, with centuries of cumulative torque leaving it poised for sudden disruption. Radiation pressure, particularly from the Sun as the object approached, may have further influenced both the trajectory and the fragmentation process. For smaller fragments, even minor photon momentum can impart measurable acceleration, subtly altering the debris field's evolution. The interplay between rotational forces and radiation pressure could explain some of the irregular trajectories observed, as fragments responded differently depending on mass, shape, and reflective properties. In this context, the disintegration was not purely mechanical, but a dynamic interplay of energy and momentum acting over time. Scientists also considered the role of thermal stresses. As sunlight penetrated the body's surface, internal temperature gradients could generate differential expansion, particularly if the object contained layers of ice, silicates, and metal. Cracks could propagate, sometimes explosively, releasing energy in bursts that contributed to fragment acceleration. This combination of tidal, rotational, radiative, and thermal forces presented a multifactorial scenario. 3I Atlas was subject to a confluence of stresses that no single terrestrial model could fully encapsulate. Yet even these mechanisms could not account for all observations. Some fragments exhibited acceleration or directional deviations inconsistent with classical physics, suggesting that unknown forces, perhaps related to interstellar medium interactions or exotic material properties, played a role. The cosmic forces at work on 3I Atlas, then, were both familiar and mysterious, a reminder that even well-understood principles can produce outcomes that challenge intuition when applied to objects shaped by eons of interstellar history. The shattering of 3I Atlas was a testament to the delicate balance of forces in the cosmos, where the invisible pressures of gravity, light, and motion can converge to transform a solitary wanderer into a scattering storm of cosmic fragments. As the fragmentation unfolded, the scientific community found itself divided, not by the data which was copious and precise, but by interpretation. Astrophysicists debated whether the breakup of 3I Atlas could be entirely explained by natural processes, or whether unknown, more exotic mechanisms must be invoked. Some argued that cumulative tidal stress, rotational spin-up, and thermal gradients sufficed to explain the dispersal. Others, however, pointed to anomalous acceleration of fragments, unusual composition, and erratic brightness patterns as evidence that conventional physics alone could not fully account for the observed behavior. The debate was amplified by the unprecedented accessibility of data. Observatories shared high-resolution imagery, spectral readings, and trajectory models in near real time, allowing teams across the globe to analyze and simulate possible scenarios. Conferences and online forums became arenas of rigorous discussion, with theoretical physicists, planetary scientists, and comet specialists weighing the probability of each hypothesis. Some researchers proposed that interactions with the interstellar medium low-density gas, cosmic rays, or magnetic fields could exert subtle but significant forces over the object's long journey, potentially priming it for sudden fragmentation. Other voices speculated on the object's origin and internal composition as critical factors. If 3I Atlas contained heterogeneous materials, pockets of volatile compounds, or embedded metallic inclusions, the internal stress landscape could be far more complex than that of typical solar system comets. Fragmentation patterns, in this context, might reflect not a simple mechanical failure, but a cascade of reactions within a delicately balanced interstellar structure. The interplay of these variables produced a scientific dialogue characterized by both rigor and imagination, a recognition that the universe can present situations that stretch beyond prior experience. The discord extended to predictive modeling. While some simulations suggested that the debris cloud would largely disperse harmlessly, others indicated a non-negligible probability of fragments intersecting planetary orbits. Even small differences in initial conditions led to dramatically different outcomes, highlighting the chaotic sensitivity of hypervelocity interstellar debris. This uncertainty underscored a broader philosophical tension. The more precisely humanity observes, the more apparent the limitations of its understanding become. Ultimately, the escalating scientific debate illuminated not only the complexity of 3I Atlas, but also the vitality of collaborative investigation. The fragmentation challenged assumptions, forced the refinement of models, and revealed gaps in existing theories of interstellar dynamics. In wrestling with the object's enigmatic behavior, scientists confronted the very edge of human knowledge, navigating between the confidence of calculation and the humility demanded by a universe that refuses to be fully anticipated. The shattering of 3I Atlas thus became a catalyst for both empirical inquiry and intellectual introspection, a reminder that cosmic mysteries can provoke both revelation and uncertainty. High-resolution imaging of 3I Atlas's fragments unveiled a level of intricacy that deepened the mystery. The surfaces of individual pieces were not uniform. Instead, they displayed a labyrinth of ridges, craters, and layered deposits that suggested a complex geological history. Some areas appeared polished, reflecting sunlight with an unexpected intensity, while others were matte, absorbing radiation in ways that created sharp thermal contrasts. The intricate textures hinted at processes spanning millions of years, from cosmic ray bombardment to thermal cycling across interstellar distances. Scientists noted subtle stratifications within the debris, visible in both spectral data and direct imaging. These layers suggested the object had undergone differentiation, separating into zones of varying density and composition, a process more typically associated with planetary bodies than small cometary objects. The implications were profound. 3I Atlas may have originated in a protoplanetary disk where heating, accretion, and chemical segregation shaped its structure long before it embarked on its interstellar journey. Each fragment was a preserved record, a cross-section of another world's formation history. The cratered surfaces also told a story of collisions and cosmic wear. Micrometeoroid impacts over eons had sculpted pockmarks of various sizes, while some depressions hinted at previous episodes of volatile-driven outbursts. Certain ridges and fractures appeared oriented along stress lines, suggesting that rotational forces or tidal interactions had influenced the object's internal integrity. High magnification imaging revealed the presence of fine particulate coatings, possibly residues of evaporated ices, lending further complexity to the fragment surfaces. These revelations had practical implications for trajectory modeling. Surface heterogeneity and differential reflectivity affect how solar radiation pressure acts on fragments, subtly altering their motion over time. Uneven heating could produce asymmetric outgassing, generating small but cumulative thrusts that modified the path of each piece. For astronomers attempting to predict potential planetary intersections, understanding these micro-variations became essential. Each observation, each new layer resolved in images, fed into increasingly sophisticated simulations designed to anticipate how the fragments would navigate the solar system. The hidden complexity revealed by imaging also carried philosophical weight. 3. I-Atlas was no longer merely a point of light or a fragmented object. It was a living record of interstellar processes, an archive of cosmic history traveling through the void to impart lessons about formation, resilience, and change. Every ridge, every crater, every reflective patch was a testament to the intricate forces shaping the universe, preserved over unimaginable distances and timescales, now revealed to humanity through the lens of patient observation and technological precision. Among the most striking discoveries was the unprecedented speed and acceleration of certain 3I-Atlas fragments. Observational data revealed that some pieces were moving significantly faster than models predicted, suggesting influences beyond simple gravitational mechanics or standard outgassing. These accelerations were not uniform. Fragments traveling in similar trajectories often diverged unexpectedly, while others, initially following erratic paths, suddenly stabilized along new vectors. The magnitude and variability of these velocities challenged existing frameworks for interstellar object dynamics. Astronomers employed precise astrometric measurements to quantify these motions. By tracking changes in position relative to background stars, scientists calculated velocities exceeding those typical for solar system comets by factors of 2 to 3. Even after accounting for radiation pressure, rotational forces, and the gravitational pull of the Sun and planets, discrepancies persisted. These high-velocity fragments implied either an internal source of kinetic energy, perhaps stored in pressurized volatile pockets, or interaction with previously unconsidered external forces, such as charged particle fluxes or micromagnetic fields within the solar system. The acceleration also complicated predictions for planetary intersections. Small deviations in velocity translate to significant changes in trajectory over astronomical distances, and fragments moving faster than expected increased the urgency for monitoring. Scientists updated models daily, recalculating orbital paths, estimating probabilities of close approaches to Earth, Mars, and other inner solar system bodies. Each refinement underscored the sensitivity of celestial mechanics when confronted with high-speed, low-mass interstellar debris. Furthermore, the velocities carried implications for understanding the origin and history of 3I-Atlas. Interstellar travel exposes objects to cosmic radiation, sparse gas, and gravitational perturbations from numerous stellar encounters. The observed accelerations could reflect cumulative effects of such long-term influences preserved and amplified during the fragmentation process. Alternatively, they might indicate previously unrecognized properties of the object's material composition, metallic or crystalline domains, capable of storing and releasing energy in ways unfamiliar to solar system analogues. Ultimately, these observations reinforced the notion that 3I-Atlas was exceptional, not merely in size or trajectory, but in its dynamic behavior. Each high-velocity fragment was a messenger from a distant system, carrying both the scars and the energies of its interstellar voyage. Scientists faced a dual challenge: to unravel the physical mechanisms behind these accelerations and to anticipate the potential consequences as the fragments raced through the solar system, offering a rare, if unsettling, opportunity to witness interstellar physics in real time. In their quest to explain 3I-Atlas's extraordinary behavior, scientists turned to theoretical models that extended beyond conventional cometary physics. One avenue explored the influence of dark matter, the elusive and invisible substance thought to pervade the galaxy. Though its interactions with ordinary matter are extremely weak, researchers speculated that the cumulative effect over millions of years could subtly alter trajectories, perhaps contributing to the anomalous acceleration observed in certain fragments. While direct evidence remained elusive, such considerations reflected the need to integrate cosmological context into localized observations. Cosmic radiation, another interstellar factor, offered a more tangible explanation. High-energy particles constantly bombard objects traveling through space, inducing chemical changes and surface erosion over millennia. For 3I Atlas, the differential exposure across its body might have created zones of variable structural integrity, producing the irregular fragmentation pattern observed. Some theorists modeled these cumulative effects, suggesting that even minor differences in particle flux could lead to catastrophic failure when combined with rotational stress or tidal forces during solar system entry. Other scientists examined weakly interacting massive particles, WIMPs, as a speculative mechanism. If portions of 3I Atlas contained concentrations of exotic matter, interactions even rare could release energy sufficient to affect fragment velocities. Though highly theoretical, these models were considered due to the inability of standard physics alone to account for the full range of observed motion. The presence of unusual metallic and crystalline compounds in spectroscopy added further incentive to explore these more speculative explanations. Einstein's relativity and the principles of gravitational interaction were revisited in the context of high-speed fragments. Hyperbolic trajectories approaching solar velocities required precise calculations of time dilation effects, energy distribution, and momentum transfer, particularly as fragments accelerated under non-uniform forces. Incorporating relativistic corrections refined predictions of fragment paths, underscoring the importance of accounting for both classical and modern physics in modeling such interstellar encounters. Finally, cosmic inflation and multi-field quantum theories provided broader philosophical frameworks. While not directly testable in the case of 3I Atlas, they offered conceptual scaffolding to contemplate how objects from distant star systems might carry properties shaped by exotic physics, hidden dimensions, or early universe conditions. In synthesizing these theories, scientists were not merely attempting to solve a practical problem of trajectory or composition. They were confronting the edges of knowledge itself, using the fragmented remains of an interstellar wanderer as both data and inspiration for speculative yet grounded physics. In response to the escalating mystery, international observatories and space agencies mobilized with unprecedented coordination. NASA, ESA, and a network of independent observatories pooled their resources to track, analyze, and model the dispersing fragments of 3I Atlas in real time. Observatories from Mauna Kea to La Silla synchronized observations to ensure continuous coverage, while automated sky surveys scanned for smaller debris that might otherwise elude detection. The collaborative effort represented one of the most extensive monitoring campaigns of an interstellar object in history. Satellite missions contributed critical data. The Hubble Space Telescope provided high-resolution imaging, capturing surface textures and fragment separation sequences, while the James Webb Space Telescope offered infrared insights into thermal properties, revealing internal structures and potential volatile content. Ground-based radar systems tracked fragment velocities, refining orbital models and enabling predictions of close approaches with inner solar system planets. Even amateur astronomers, equipped with high-quality telescopes and coordinated through scientific networks, supplied valuable observations, demonstrating the democratization of astronomical monitoring in the modern era. The international scientific community organized around rapid data sharing and joint analysis. Virtual collaboration platforms allowed teams across continents to exchange spectroscopic readings, light curves, and trajectory updates in near real time. This global effort accelerated model refinement, enabling simulations that incorporated fragment acceleration, rotation, compositional heterogeneity, and radiation pressure. Each adjustment brought predictive accuracy closer to the reality of 3I Atlas's behavior, although uncertainty remained inherent due to the chaotic dynamics of the dispersing debris cloud. Beyond tracking, observatories deployed targeted observation campaigns to probe fragment composition. Spectral analysis focused on detecting isotopic anomalies, metallic inclusions, and organic compounds, while photometric studies measured light reflection and absorption to infer surface structure. Advanced computational models integrated these observations, allowing scientists to simulate potential fragmentation cascades and estimate kinetic energy distributions among the debris. This holistic approach blended empirical measurement with theoretical modeling, seeking to reconcile observation with prediction. The mobilization also highlighted the human element. Scientists worked around the clock, interpreting data, adjusting models, and publishing preliminary findings. Conferences, live discussions, and collaborative papers reflected a high-stakes endeavor, one driven not only by curiosity, but by the recognition that fragments of 3I Atlas were moving toward planets, including Earth and Mars, however small the probabilities. In this convergence of technology, expertise, and urgency, humanity witnessed the capacity of international collaboration to confront the mysteries of the cosmos, observing a cosmic event as it unfolded and adapting in real time to the challenges posed by a shattered interstellar visitor. Amid the technical data and predictive models, the human dimension of the 3I Atlas investigation became increasingly pronounced. Astronomers, astrophysicists, and planetary scientists found themselves at the intersection of intense observation and emotional engagement. For many, the event was the culmination of decades of work, an extraordinary alignment of experience, technology, and cosmic happenstance. Profiles emerged of key scientists, those who first identified the fragmentation, those who calculated trajectories in sleepless nights, and those who coordinated global networks to ensure comprehensive coverage. Their dedication reflected not only professional rigor, but a profound sense of wonder and responsibility. These scientists navigated a dual reality. On one hand, they faced the meticulous demands of data analysis, calculating fragment velocities, refining spectral interpretations, and running complex simulations to forecast potential planetary encounters. On the other hand, they contended with the emotional weight of observing a cosmic phenomenon of unprecedented scale. The fragments of 3I Atlas were not abstract entities, they were tangible remnants of a distant system hurtling across space with histories encoded in their composition, rotation, and trajectory. Each observation was a glimpse into a universe far removed from everyday experience, yet intimately connected through the laws of physics. Collaboration introduced both challenge and opportunity. Teams spread across continents communicated through video conferences, shared databases, and instantaneous messaging platforms, navigating time zones and cultural differences to maintain continuous monitoring. Disagreements about interpretation, modeling approaches, and prioritization of observations were inevitable, yet these debates drove innovation, sharpening analytical methods and fostering new perspectives on interstellar dynamics. The human element, in this context, was inseparable from the scientific process. Intuition, experience, and judgment guided decisions as much as algorithms and telescopic measurements. The emotional resonance extended beyond the scientific community. Public interest surged, fueled by images of the fragmented debris streaking across the sky and reports of potential planetary intersections. scientists became both observers and communicators, tasked with explaining the phenomena without succumbing to sensationalism. Their narratives balanced the awe-inspiring nature of the event with sober assessments of risk, highlighting the beauty of discovery while acknowledging the uncertainties inherent in studying an interstellar object in real time. Ultimately, the human element underscored a fundamental truth. The study of 3I Atlas was not merely a technical endeavor, but a deeply human one. The convergence of curiosity, dedication, and collaboration illuminated the capacity of humans to engage meaningfully with the cosmos, to interpret signals from light years away, and to grapple simultaneously with the intellectual, emotional, and ethical dimensions of observing a universe both magnificent and indifferent. Through this lens, the fragments of 3I Atlas were not only celestial debris, they were catalysts for human reflection, resilience, and awe. As observations of 3I Atlas intensified, attention naturally turned to the potential consequences of its debris for the planets of the inner solar system. Sophisticated simulations modeled the kinetic energy, mass, and trajectories of fragments, projecting scenarios in which certain pieces could intersect with planetary orbits. While most fragments were expected to pass harmlessly through the solar system, a small subset presented theoretical risks, particularly to Mars and, in rare cases, Earth. The exercise was not mere speculation. It was a rigorous application of celestial mechanics, statistical modeling, and risk assessment. The planetary threat analysis required integrating multiple variables: fragment size, density, velocity, rotation, and trajectory all influenced the probability of impact. Even minor variations in these parameters, compounded over millions of kilometers of travel, could produce significantly different outcomes. Scientists used Monte Carlo simulations and N-body modeling to account for these uncertainties, generating thousands of potential scenarios to assess impact probabilities. The results, while mostly reassuring, underscored the unpredictable nature of interstellar debris. A single fragment, even small, could carry sufficient energy to create observable effects on planetary surfaces or atmospheres. Mars emerged as a particularly interesting case. Its thin atmosphere and lower gravity meant that small to medium-sized fragments could reach the surface with less atmospheric deceleration than on Earth. While catastrophic impacts were unlikely, surface strikes could generate localized shockwaves, ejecta, or meteor-like phenomena observable by orbiters and rovers. Earth, with its denser atmosphere and magnetic shielding, would likely see most fragments burn up upon entry, producing meteor showers of unusual composition and potentially spectacular brightness. The unpredictability of fragment composition, including metallic or highly reflective materials, added a layer of uncertainty to both observational planning and risk assessment. The scenario also highlighted the broader implications for planetary defense. While existing monitoring systems are designed primarily to track asteroids and near-Earth objects originating from within our solar system, interstellar debris presents a novel challenge. High velocities and atypical compositions complicate both detection and mitigation strategies. The arrival of 3 ATLAS fragments underscored the need for adaptable monitoring frameworks capable of rapidly integrating new observational data and revising predictions in real time. Ultimately, modeling the potential planetary consequences of 3I Atlas emphasized both the scale and the subtlety of interstellar interactions. These fragments were not merely scientific curiosities, they represented tangible reminders that the solar system exists within a broader galactic environment. Each trajectory, each calculated impact probability, illustrated the delicate interplay between cosmic chance and celestial mechanics, reinforcing the profound interconnectedness of our planetary neighborhood with the vast, largely unseen universe beyond. Beyond trajectories and potential impacts, scientists intensified the chemical and spectral analysis of three I-Atlas fragments, seeking to uncover the elemental and molecular story carried from its parent system. Spectroscopy revealed unusual isotopic ratios, hinting at a formation environment distinct from that of typical solar system comets. Some fragments contained isotopes of oxygen, carbon, and nitrogen in proportions that suggested the object had originated in a stellar nursery where conditions, temperature, pressure, and radiation differed significantly from those near the Sunday. Each detection became a clue to the cosmic environment that forged this interstellar traveler. The discovery of rare metallic compounds within the debris further deepened the mystery. Analyses identified reflective crystalline structures interspersed with amorphous metallic phases, materials rarely observed in naturally occurring solar system bodies. Their presence suggested a history of intense thermal processing or prolonged exposure to radiation fields capable of inducing unusual crystallization. These compounds could also account for some of the anomalous acceleration observed in specific fragments, as differences in density and reflectivity alter the way radiation pressure acts upon them. Organic compounds were also detected in surprising abundance. Complex hydrocarbons, including polycyclic aromatic hydrocarbons, PAHs, indicated that chemical processes within three I-Atlas had been active over long timescales, producing molecules that in other contexts are associated with prebiotic chemistry. The combination of organics, metals, and unusual isotopes created a composite profile unlike any single solar system comet, hinting at processes that may have been unique to its originating stellar system. Researchers considered whether these materials could shed light on the broader question of the distribution of organic molecules across the galaxy and their role in potential prebiotic chemistry on distant worlds. High-resolution spectroscopy also allowed the detection of minute differences between fragments. While some pieces exhibited strong metallic signatures, others were dominated by ices or organics, suggesting an intricate internal layering of the parent body. This heterogeneity had profound implications for modeling both fragmentation mechanics and future debris evolution. Fragments with higher metal content, being denser, would maintain momentum differently than lighter, ice-rich counterparts, leading to divergence in trajectories and a complex, three-dimensional dispersal pattern that challenged prediction models. These analyses elevated the scientific significance of three I-Atlas beyond mechanics and trajectory. Each fragment carried a chemical narrative, a record of formation conditions, radiation exposure, and interstellar history. By studying them, scientists gained insights not only into a single object, but also into the broader processes that govern material exchange between stars and the chemical evolution of the galaxy. In essence, the shattered fragments became emissaries from another system, delivering both data and cosmic context across unimaginable distances and reminding humanity of the intricate, interconnected nature of matter throughout the cosmos. With composition and trajectories under scrutiny, scientists turned to advanced simulations and predictive modeling to anticipate the future behavior of three I-Atlas fragments. High-performance computing clusters ran thousands of iterations, incorporating variables such as fragment mass, shape, reflectivity, rotation, and potential outgassing. Monte Carlo simulations allowed researchers to explore a vast parameter space, identifying probable paths and quantifying uncertainties in fragment dispersal. These models provided probabilistic forecasts rather than deterministic ones, reflecting the chaotic dynamics inherent to a shattering interstellar object. simulations revealed intriguing patterns. Larger, denser fragments tended to maintain straighter trajectories, less affected by solar radiation pressure, while smaller, more irregular pieces exhibited highly variable motion. Interactions between fragments, although minimal due to the vast distances separating them, were also modeled. Gravitational nudges among larger fragments could slightly alter paths, compounding long-term unpredictability. By iteratively refining the models with real-time observational data, astronomers gradually improved the accuracy of predicted positions and potential planetary encounters. The predictive efforts extended beyond trajectory to include kinetic energy distributions. By calculating fragment mass and velocity, scientists estimated potential energy upon atmospheric entry for Earth-bound or Mars-bound fragments. While catastrophic collisions remained highly unlikely, the simulations allowed planners to anticipate meteor shower intensity, brightness, and duration. These models also informed observational campaigns, guiding telescope time allocation to monitor fragments most likely to produce notable phenomena. Computational modeling also served as a tool for testing theoretical mechanisms behind fragmentation. By varying assumptions about internal stresses, rotational spin-up, and thermal gradients, researchers could compare simulated breakup patterns to observed data. These comparisons provided indirect validation of hypotheses regarding the forces acting on 3I atlas, helping to distinguish between purely mechanical explanations and more exotic influences. Each simulation, in effect, became an experiment in cosmic mechanics, translating abstract physics into concrete, testable predictions. Ultimately, the simulations underscored the interplay between observation and theory. Real-time data fed into computational models, which in turn refined expectations for both fragment motion and potential planetary interactions. This iterative process highlighted the sophistication of modern astrophysics, where observation, theory, and high-speed computation converge to confront phenomena of unparalleled complexity. Through these simulations, scientists glimpsed not only the immediate behavior of 3I atlas fragments, but also broader insights into the dynamics of interstellar debris, offering a window into processes that shape our galaxy in ways only recently accessible to human inquiry. Speculation about the interstellar origin of 3I atlas intensified as observational data accumulated. Its hyperbolic trajectory clearly indicated that it was not gravitationally bound to the Sun, yet questions lingered. From which star system had it come, and under what circumstances had it been ejected into interstellar space? Astronomers traced its incoming path backward, using orbital dynamics to approximate potential source regions. While pinpointing a precise origin proved impossible due to cumulative gravitational perturbations and observational uncertainties, certain stellar neighborhoods emerged as plausible birthplaces, dense star clusters, or regions with significant planet-forming activity. The chemical and isotopic composition of the fragments provided additional clues. Unusual ratios of oxygen, carbon, and nitrogen suggested formation in a system with distinct nucleosynthetic processes, potentially differing from those typical of our local stellar neighborhood. Metallic inclusions and crystalline structures hinted at thermal histories involving heat sources more intense than solar radiation alone, perhaps near a young, massive star or within a protoplanetary disk experiencing episodic heating events. This reinforced the notion that 3I atlas carried with it a tangible record of processes occurring light-years away, bridging human observation with environments otherwise inaccessible. Astrophysicists also considered the dynamics that could have propelled 3I atlas from its home system into interstellar space. Close gravitational encounters with giant planets, multi-body interactions, or even stellar flybys could have imparted sufficient velocity to escape a parent star's gravitational well. Such mechanisms are rare but not implausible, and they underscore the vast scale and complexity of interstellar object dynamics. In this light, 3I Atlas was both messenger and survivor, a body forged under alien conditions, expelled across the void, and now entering a solar system far from its birthplace. Speculation extended to the possibility that the parent system had undergone extraordinary events. Supernovae, stellar mergers, or intense radiation episodes could have altered the object's structure, composition, or trajectory before ejection. While these scenarios remained hypothetical, they provided plausible explanations for the unusual structural integrity, heterogeneous composition, and unexpected accelerations observed in the fragments. Each line of reasoning combined astrophysical modeling with empirical observation, reflecting the iterative nature of understanding a phenomenon that is both remote and immediate. In contemplating its interstellar origin, scientists were confronted with a profound narrative. 3I Atlas was more than debris. It was a traveler bearing the chemical and mechanical imprint of a distant world. Its arrival and subsequent fragmentation offered humanity a rare opportunity to study material forged under alien conditions, revealing not only the physics of interstellar transit, but also the interconnectedness of stellar systems across the galaxy. Each fragment was a piece of a cosmic story, billions of years in the making, arriving in our observational grasp as a reminder of the vast, dynamic, and historically rich universe in which we reside. The unusual composition of 3 Atlas fragments prompted consideration of exotic materials and structures. Among the most intriguing discoveries were metallic alloys embedded within icy matrices, materials that were highly reflective, crystalline, and sometimes amorphous, suggesting formation under conditions of extreme pressure or radiation. Such compounds are rare in known solar system comets and asteroids, implying that 3I Atlas had experienced processes or environments not typical in our neighborhood. The presence of these materials also provided a potential explanation for some anomalous acceleration patterns, as reflective or metallic surfaces interact differently with solar radiation and particle flux. Analyses revealed fine stratifications and heterogeneous layering, with some fragments dominated by metals and others rich in volatile ices or complex organics. This variation indicated that the parent body had undergone internal differentiation, perhaps forming in a protoplanetary disk with diverse thermal and chemical zones. The layers suggested a history of repeated heating and cooling, radiation exposure, and possibly impact events, forming an intricate internal architecture. Understanding this composition was crucial not only for interpreting fragmentation mechanics, but also for modeling how each fragment would respond to forces during its transit through the solar system. Speculative models proposed the existence of amorphous crystalline structures capable of storing internal stresses over long periods. Such structures, when suddenly relieved during fragmentation, could release bursts of energy that contribute to unexpected fragment acceleration. In some cases, spectroscopic signatures hinted at organometallic compounds that might be unstable under solar radiation, leading to micro-explosive events upon exposure. While highly theoretical, these possibilities offered plausible explanations for patterns otherwise inexplicable by classical cometary physics. The exotic nature of 3I Atlas's materials also sparked broader scientific curiosity. If these fragments contained isotopic or elemental signatures unique to their parent system, they could offer unprecedented insights into the diversity of planetary formation across the galaxy. Organic compounds embedded within metallic matrices raised questions about the distribution of prebiotic molecules beyond our solar system and the potential for chemically complex materials to survive interstellar journeys intact. Each fragment became a laboratory in miniature, providing clues to the chemistry, physics, and history of distant star systems. In sum, the exotic material hypothesis reinforced a central theme. 3I Atlas was not merely an interstellar visitor, but a messenger from another cosmic environment, carrying within its fragments both the physical traces of its formation and the narrative of an alien system's history. Every reflective surface, every stratified layer, and every anomalous spectral line was a testament to processes and forces operating far beyond human observation, now unveiled through meticulous study of its shattering and debris. Beyond physical composition, some researchers explored whether quantum or relativistic effects could have influenced 3I Atlas's fragment behavior. While the fragments were not moving near the speed of light, their hyperbolic trajectory, combined with minute accelerations, raised questions about subtle relativistic corrections. Gravitational time dilation, momentum transfer at high velocities, and the influence of solar gravitational potential on rapidly moving, heterogeneous fragments were all considered in advanced modeling. Though minor in magnitude, these relativistic factors could slightly adjust predicted trajectories, adding complexity to the already chaotic dynamics. Quantum effects, though even more speculative, were examined in the context of material properties. Certain crystalline structures observed in fragments displayed unusual electron configurations or lattice arrangements that might respond differently to cosmic radiation or magnetic fields. Researchers hypothesized that such properties could, in rare circumstances, contribute to microscale energy release or fragment propulsion. While these ideas remained theoretical, they underscored the degree to which 3I Atlas challenged conventional assumptions about interstellar objects and the need to consider processes at both macroscopic and microscopic scales. Additionally, the potential influence of weak interactions, forces beyond the electromagnetic, gravitational, and strong nuclear interactions, was contemplated. Could rare, low-probability particle interactions over the course of millions of years subtly alter internal stress distributions or surface charges, priming the body for catastrophic fragmentation? While impossible to test directly with current instruments, such hypotheses illustrated the lengths to which scientists were willing to explore when confronted with phenomena that eluded standard explanations. These considerations were not merely abstract. Incorporating relativistic and quantum perspectives into trajectory models allowed researchers to marginally refine predictions of fragment paths and collision probabilities. Even a small adjustment could differentiate between a harmless flyby and a potential planetary intersection. In essence, these speculative frameworks served as supplementary lenses, highlighting potential influences invisible under classical mechanics, yet significant when modeling the intricate dance of high-velocity, heterogeneous interstellar debris. Ultimately, the exploration of quantum and relativistic effects reinforced the larger lesson of 3I Atlas, that interstellar objects, forged in distant systems and subjected to forces beyond our direct experience, may exhibit behaviors that blend classical, relativistic, and quantum phenomena. Each fragment became a nexus where the micro and macro scales of the universe converged, offering scientists an unparalleled, if challenging, opportunity to probe the subtleties of physics on a galactic stage. The extraordinary challenge posed by 3I Atlas fostered unprecedented international collaboration. Teams spanning continents, institutions, and disciplines worked in concert, sharing observations, computational models, and theoretical insights. Data pipelines connected telescopes in Chile, Hawaii, Spain, and Australia, enabling near-continuous tracking of fragment positions, velocities, and compositional variations. This cooperative effort transformed what might have been isolated studies into a global enterprise, with scientists responding in real time to a constantly evolving cosmic event. Shared databases allowed researchers to compare spectral signatures, brightness variations, and trajectory deviations across fragments. Discrepancies between instruments were quickly reconciled, and models were iteratively updated as new measurements arrived. This dynamic collaboration not only improved predictive accuracy but also fostered cross-disciplinary insights, merging expertise from astrophysics, planetary science, materials chemistry, and computational physics. Debates over interpretations, once confined to individual labs, now unfolded in international forums, webinars, and secure collaborative platforms. The human element of coordination was profound. Teams maintained around-the-clock vigilance, often across time zones, analyzing data and refining models to ensure comprehensive coverage. Amateur astronomers contributed supplemental observations, their findings integrated seamlessly into professional analyses. The cumulative effort exemplified the synergy possible when technological capability and human dedication converge, demonstrating the power of global scientific networks to respond to emergent phenomena with precision and agility. This collaboration extended beyond immediate observational needs. The shared knowledge fostered rapid exploration of theoretical frameworks, from conventional mechanical explanations to exotic physics and chemical modeling. Scientists collectively evaluated the plausibility of multiple hypotheses, iterating on simulations to reconcile discrepancies between observed fragment behavior and predicted dynamics. The result was a living, adaptive understanding of 3I Atlas, continually refined as the object and its fragments continued their journey through the inner solar system. Ultimately, international collaboration revealed a deeper truth. The study of 3I Atlas was not merely about collecting data on a single interstellar object, but about cultivating a global scientific consciousness capable of responding to the universe's complexities. The fragments, scattered across space, became a unifying focal point for humanity's curiosity and ingenuity, demonstrating that even in the face of unprecedented cosmic challenges, collective effort could illuminate the unknown. Amid the technical and observational rigor, a philosophical reflection began to emerge within the scientific community. The fragmentation of 3I Atlas offered more than data. It presented a profound meditation on humanity's place in the cosmos. Observing an interstellar object, forged in a distant system and traveling light years to arrive within the solar system, underscored the vastness and indifference of the universe. Each fragment, moving inexorably along its trajectory, was a silent testament to the forces that shape matter across unimaginable distances and timescales. This contemplation was intensified by the unpredictability of the debris. While human intellect and technology could measure, model, and simulate, the inherent uncertainty of fragment paths served as a humbling reminder of limits in knowledge and control. The universe, in its scale and complexity, does not conform to expectations. It operates independently of human concerns. The shattering of 3I Atlas thus became a mirror, reflecting not only the physical processes at work, but the philosophical realities of existence, our relative fragility, our observational limitations, and the fleeting window through which we glimpse cosmic events. The reflective dimension extended to the temporal scale. Fragments had been shaped over millions of years, their materials forged in the furnace of stellar processes, sculpted by radiation, collisions, and gravitational interactions. For humanity, Encountering these fragments even briefly is a profound convergence of cosmic and human timescales. The recognition that we can study, yet never fully control, such phenomena emphasizes the delicate balance between curiosity and humility, between understanding and wonder. Additionally, 3I Atlas's arrival inspired questions about interconnectivity in the galaxy. A single object, traveling for millennia, carries chemical, structural, and historical information across light years, linking distant star systems to our own. Its fragments, now dispersed through our solar system, are not merely objects of scientific study, they are messengers, bearing witness to cosmic processes beyond direct observation. In this sense, the interstellar visitor becomes both teacher and catalyst, prompting reflection on the universality of physical law, the randomness of cosmic events, and the enduring capacity for life and intelligence to seek comprehension amidst uncertainty. Thus, amid calculations, simulations, and spectral analysis, the human mind could not help but pause, absorbing the emotional resonance of the encounter. The fragmented 3I Atlas was more than a scientific curiosity. It was an invitation to reckon with the scale, beauty, and fragility of existence, to find meaning in observation, and to confront the philosophical dimensions of our place within the infinite expanse of the universe. Speculation inevitably turned toward the future. Scientists and philosophers alike contemplated what the arrival of 3I Atlas fragments meant for long-term interstellar interactions with our solar system. While the immediate threat to Earth or Mars remained low, the broader implication was clear. The solar system exists within a dynamic galactic environment, where objects from distant stars can traverse light years and enter our planetary neighborhood with little warning. This reality prompted reflection on the potential frequency of such events and the importance of developing adaptive monitoring systems capable of rapid response. Extrapolating from 3I Atlas, theorists considered a spectrum of possible future encounters. Some interstellar objects might be smaller, less massive, and harmless, passing through unnoticed except by sensitive instruments. Others, perhaps larger or moving at higher velocities, could pose significant challenges, from generating intense meteor showers to potential planetary impacts. Understanding the behavior, composition, and trajectories of such objects became a matter of not only scientific curiosity, but also planetary stewardship. The events surrounding 3I Atlas offered a case study in preparedness, highlighting the need for predictive frameworks, international coordination, and rapid data assimilation to mitigate potential hazards. The discussion also encompassed the broader astrophysical consequences. Interstellar debris carries information about the formation processes, chemical environments, and dynamical histories of other star systems. Each arrival offers a rare opportunity to study matter originating beyond the Sun's influence, providing comparative data for understanding planetary formation, chemical evolution, and the distribution of organic compounds across the galaxy. In this sense, future encounters could serve as both scientific treasure troves and natural experiments in galactic chemistry and dynamics. Philosophically, the potential for recurring interstellar arrivals evokes contemplation of the solar system as a semi-permeable boundary, a stage where matter from distant stars occasionally intersects with local dynamics. Each object that arrives carries both history and possibility, remnants of distant worlds, repositories of chemical information, and testaments to forces acting across scales and epochs. 3I Atlas, in its violent fragmentation and high-velocity dispersal, exemplifies both the opportunities and uncertainties inherent in these encounters. Ultimately, considering future interstellar interactions reinforces a dual perspective. The universe is both generative and indifferent, offering unprecedented insight while demanding respect for uncertainty. Humanity's challenge is to observe, model, and learn from these transient visitors, integrating empirical knowledge with philosophical reflection and preparing for the inevitable recurrence of such cosmic events. Each fragment from 3I Atlas racing through space is both a messenger and a harbinger, reminding us that the cosmos is an ever-changing environment in which even distant objects can intersect with our planetary experience in profound ways. In parallel with observation and speculation, attention turned to practical measures for planetary defense. While the likelihood of catastrophic impact from 3I Atlas fragments was low, the event served as a powerful impetus for evaluating the readiness of existing systems. Agencies such as NASA and ESA reviewed current detection capabilities, trajectory modeling techniques, and mitigation protocols to assess how well humanity could respond to interstellar debris. The arrival of high-velocity fragments underscored limitations in early warning networks, primarily designed for near-Earth objects originating within the solar system. Technologies under consideration ranged from enhanced surveillance to active mitigation strategies. Space-based telescopes with high temporal and spatial resolution were prioritized to detect small, fast-moving fragments before they entered sensitive orbital regions. Advanced computational models were deployed to refine predictions of fragment trajectories and potential impact zones. Some hypothetical strategies involved deflection techniques, such as deploying kinetic impactors to alter the path of larger fragments, or laser ablation to induce subtle trajectory changes over time. Although these approaches remained largely theoretical for interstellar debris, 3I Atlas provided a compelling case study for their development. Coordination among international bodies became essential. The interstellar nature of the debris meant that fragments could approach from unexpected angles and velocities, making rapid data sharing and synchronized observation crucial. Collaborative frameworks allowed nations to combine telescope networks, computational resources, and expertise to enhance detection capabilities and refine response strategies. Workshops and simulation exercises explored what-if scenarios, evaluating the effectiveness of existing planetary defense measures against high-speed, heterogeneous interstellar fragments. These preparatory measures carried scientific as well as practical benefits. Monitoring fragments for trajectory correction experiments or debris characterization allowed for refinement of physical models, improving understanding of fragment response to forces such as radiation pressure, spin-up, and gravitational interactions. In this sense, planetary defense and fundamental research became intertwined, each informing the other in a real-time experiment orchestrated by necessity. Ultimately, the arrival of 3I Atlas fragments highlighted the necessity of preparedness, flexibility, and proactive planning. While catastrophic outcomes were unlikely, the event reinforced the need for robust observational infrastructure, advanced modeling, and international collaboration. Humanity's engagement with interstellar debris is both a practical exercise in planetary stewardship and an opportunity to expand scientific understanding, bridging the immediate challenge of potential hazards with the broader quest to comprehend the dynamic environment of our galactic neighborhood. Despite extensive observation, analysis, and modeling, the behavior of 3I Atlas remained enigmatic. Even as astronomers refined trajectories, mapped fragment dispersal, and characterized composition, fundamental questions persisted. How exactly did the parent body survive millennia of interstellar travel only to shatter so violently? What internal or external forces triggered the fragmentation at this precise moment? And why did the fragments accelerate and diverge in ways that challenged conventional models? Each new observation answered some questions while deepening others, reinforcing the sense that the object's full story might remain elusive. The persistence of mystery underscored the limits of human knowledge in the face of cosmic complexity. While models incorporating tidal stress, spin-up, radiation pressure, and exotic material properties could approximate observed behavior, discrepancies persisted. High-velocity fragments defied simple categorization, and unusual spectral signatures resisted straightforward interpretation. Scientists were forced to accept that, despite technological prowess and theoretical sophistication, the universe could produce phenomena that elude complete understanding. 3I Atlas was a living reminder of the provisional nature of scientific knowledge, a puzzle whose pieces offered insight without total resolution. The enigmatic nature of the object also highlighted the need for humility in scientific inquiry. Researchers recognized that assumptions rooted in solar system experience might not apply universally. Interstellar objects, shaped in alien systems and subjected to forces over millions of years, could manifest behaviors unanticipated by models calibrated on familiar comets and asteroids. Each fragment of 3I Atlas thus became both data point and cautionary tale, observable, measurable, and yet irreducibly complex, a testament to the unpredictable consequences of cosmic history. In practical terms, the unresolved aspects of 3I Atlas informed ongoing monitoring strategies. Scientists maintained vigilant observation, tracking even minor deviations and recalibrating models to account for anomalies. The process became a dynamic feedback loop. Observation informs theory, theory guides observation, and each iteration refines understanding while acknowledging uncertainty. In this interplay, the fragments were not only physical entities, but also catalysts for intellectual evolution, challenging humanity to expand the boundaries of comprehension and adapt methods to meet the complexities of the cosmos. Ultimately, the persistence of mystery reinforced the profound significance of 3I Atlas. Its fragmentation was not merely an event to be catalogued, it was an encounter with the unknown, a reminder that the universe contains layers of complexity, history, and forces that stretch beyond current understanding. Even as some answers emerged, the object's behavior preserved a core of uncertainty, ensuring that it would remain a focal point of inquiry, reflection, and wonder for years to come. Beyond the immediate observations and fragment trajectories, the broader scientific implications of 3I Atlas became increasingly evident. Its arrival and fragmentation offered a unique case study for astrophysics, planetary science, and interstellar chemistry, providing empirical data to refine models of object formation, interstellar travel, and material resilience. For planetary defense, the event highlighted the necessity of adaptable monitoring systems capable of addressing high-velocity, heterogeneous debris originating from outside the solar system. Lessons learned from this encounter would inform preparedness for future interstellar visitors, guiding the development of detection, tracking, and potential mitigation strategies. In astrophysics, the unusual properties of the fragments challenged conventional assumptions about the structure and composition of small bodies. Observations of metallic inclusions, layered internal structures, and unexpected acceleration offered insights into processes occurring in distant stellar environments. The data provided a comparative framework to study the diversity of planetary formation across the galaxy, complementing studies of solar system comets and asteroids. By examining material from an alien system, scientists could probe nucleosynthesis, chemical evolution, and the survival of organics under interstellar conditions, expanding our understanding of cosmic material cycles. The event also influenced computational and theoretical modeling. Simulations developed to track fragment dispersal, account for anomalous acceleration, and predict potential planetary intersections. Improved algorithms applicable to other high-velocity or chaotic systems. These models contributed not only to observational planning, but also to broader studies of interstellar object dynamics, helping scientists anticipate the behavior of future visitors and refine our understanding of the forces acting on small bodies traveling across light years. Philosophically, the broader implications of 3I Atlas extended beyond scientific utility. The object's journey reminded humanity that the galaxy is dynamic and interconnected, with objects traversing immense distances, carrying chemical and structural histories from distant star systems. Each fragment, while physically small, symbolized the vast network of matter and energy linking disparate regions of space. Its arrival challenged anthropocentric perspectives, illustrating that cosmic processes operate on scales and timescales far beyond human experience, yet intersect intimately with our planetary neighborhood. In sum, 3I Atlas's legacy extends across disciplines, from immediate planetary defense considerations to profound contributions to astrophysics, chemistry, and cosmic philosophy. Its fragments, while transient, have provided data, inspiration, and reflection, serving as messengers from another star system and as catalysts for scientific and philosophical growth. Humanity's engagement with this interstellar visitor underscores both our vulnerability and our capacity to learn from the vast, interconnected cosmos. As the journey of 3I Atlas's fragments approached their closest approaches to the inner solar system, a sense of closure mingled with awe in the scientific community. Despite extensive tracking, simulations, and analysis, many questions remained unresolved. The exact triggers for fragmentation, the precise distribution of exotic materials, and the full impact of interstellar forces on fragment motion. Yet within this uncertainty lay profound insight. Each fragment served as a tangible connection to the cosmos, a vessel carrying the history of a distant star system across unimaginable distances. Observers reflected on the visual spectacle as well. Even as the fragments dispersed into increasingly diffuse clouds, sunlight illuminated the surfaces, revealing metallic gleams, icy layers, and organic residues. High-resolution images captured fleeting jets of gas and dust, giving the appearance of ephemeral life, as though the object, though shattered, continued to communicate through its motion and emission. The interplay of light and shadow accentuated textures invisible to the naked eye, creating a cinematic panorama that reminded astronomers of the delicate artistry of natural processes across cosmic time. Simultaneously, the event catalyzed reflection on human understanding. Models of interstellar object behavior, planetary defense protocols, and chemical analysis were all tested, improved, and sometimes challenged. The limitations exposed by 3I Atlas became instructive. Even with advanced telescopes, computing power, and collaborative networks, the universe maintains elements of unpredictability and mystery. Humanity's role is not to dominate, but to observe, interpret, and adapt, acknowledging both our capacity for insight and the vastness of the unknown. The final moments of the object's passage inspired a quiet, philosophical meditation. The fragmented debris, racing along paths shaped by distant stars and invisible forces, exemplified the transient intersection of cosmic history with human observation. For a brief span of time, fragments from light years away intersected with the sphere of human awareness, revealing complexity, fragility, and the intricate interplay of forces that govern the universe. In that intersection, observers glimpsed both the immensity of space and the poignancy of human curiosity, the desire to understand, to connect, and to find meaning amid vast, indifferent surroundings. Thus, 3I Atlas's journey concluded not with definitive answers, but with reflection, awe, and ongoing inquiry. Its fragments would continue through the solar system, imperceptible yet persistent, carrying with them the story of another system and the lessons of observation, humility, and cosmic perspective. Humanity's encounter with this interstellar visitor reaffirmed the profound beauty and complexity of the universe, a reminder that even shattered fragments can illuminate the vastness and interconnectedness of the cosmos in ways that endure long after their fleeting passage. As the last fragments of 3I Atlas receded into the depths of the inner solar system, the pace of observation gradually softened. Telescopes continued to record light curves and spectral data, but the urgency of the initial discovery gave way to contemplation. The sky, once punctuated by fleeting streaks of interstellar debris, returned to its familiar rhythm, reminding observers of the vast temporal scales on which cosmic events unfold. In this quiet, the significance of the encounter crystallized not merely in data, but in the profound reflection it inspired. The shattered fragments had traveled light years, carrying with them the history of distant stars, layered compositions, and the chemical footprints of alien systems. They had intersected, however briefly, with the human perspective, offering a window into processes otherwise inaccessible. Every measurement, every image, every calculation had been a conversation across space and time, bridging billions of years and unimaginable distances. The universe, in its immense indifference, had allowed humanity a fleeting glimpse into a story that began long before our species existed and would continue long after. In the soft aftermath, there was a sense of calm reassurance. The probabilities of impact were low, and the fragments would continue their journey, obeying the same laws that have governed matter since the formation of the galaxy. Yet their passage left a lasting impression, a reminder of vulnerability, interconnectedness, and the intricate beauty of cosmic mechanics. The event encouraged humility and wonder, prompting reflection on our place in the vast celestial arena and the delicate balance that allows life to flourish on a small pale blue dot in the immensity of space. And as the observation instruments dimmed their scrutiny, the story of 3I Atlas lingered not as a resolved mystery, but as an enduring testament to curiosity, observation, and the human desire to understand the cosmos. Its fragments may drift unseen, yet their journey continues to inspire thought, reflection, and a quiet reverence for the universe's endless, unfolding narrative. Sweet dreams.